Hi everyone, and thank you for joining us for today's webinar, which is analysing 2D soil reinforcement problems with LimitState GEO. Today's speaker is Dr. Colin Smith, and Colin is one of the originators of the DLO analysis method, which underpins LimitState GEO, and he's also the LimitState GEO product manager. Colin's going to be leading you through a short introduction to modelling 2D reinforcement in LimitState GEO and demonstrating how it can lead to far more accurate solutions than traditional analysis methods may give, while still being conceptually and practically straightforward. The webinar itself is going to run for approximately 20 to 25 minutes and will include a few minutes at the end for your questions. These can be posted in the webinar interface. We'll try to answer as many questions as we can during the time available, but this isn't always possible. We will, however, reply to any questions that you have that we don't cover in the webinar itself by email over the next few days. So without further delay, it's time to get started. So I'll pass you over to Colin.
Okay, thank you, Tom. So just to whet your appetite, we'll kick off with a slide showing a selection of problem types that can be solved by the LimitState GEO software. As you can see, the software has been designed to identify the critical collapse mechanism for any problem type in the form of a slipline mechanism. In terms of the specific content that we're going to be covering today, we're going to be looking at two-dimensional geosynthetic reinforced soil analysis with the software and how it differs from other methods and how to model a number of specific scenarios. We're also going to take a quick look under the hood to see how the software works. So to this end, I'll primarily be using the software directly to illustrate key points, but we'll make use of a few slides at the beginning and the end for an introduction and summary. And as this is a short presentation, the main aim is just to give you a flavor of what the software can do. And there won't be time to get into the details of all the software functionality. However, there will be time at the end for questions. So we'll start off with an introduction to reinforced soils and soil reinforcement types. So soil reinforcement, as I'm sure you all know, works primarily by adding a tensile strength element to the soil or equivalently transmitting one load from one part of the soil body to another. And this might be one-dimensional or two-dimensional reinforcement. So that can include things like soil nails, steel strips, geogrids, geotextiles, etc. We're going to be focusing on the two-dimensional reinforcement in this presentation. Now, there's a very large range of applications for soil reinforcement. I've given you 3 examples here. However, we'll be looking at reinforced slopes and walls using geosynthetics primarily in this presentation. Now, just to take a look at the conventional analytical approach for reinforced soils, one common approach is method of slices. So this is a limit equilibrium approach. We assume the shape of a slip surface. So on the right here, we've got a little diagram of a assumed slip circle. And we can look at the stability equilibrium of wedges of soil above that slip surface and look at the equilibrium of the forces acting on that particular slice. Now, where we have a reinforced soil body, in the lower diagram, what we have in addition is reinforcement elements at various levels that intersect that hypothetical slip surface. And in terms of looking at the stability of this slice of soil that sits above the slip surface, it's denoted by these dashed lines, where we have a reinforcement element, in order for failure to occur, that reinforcement is going to have to pull out of the sliding mass or pull out of the stationary mass. And we can calculate that to effectively calculate the pull-out force required to get that reinforcement to move. And then that additional restraining force T, in this case, can be applied to the slip circle analysis, and that then enhances stability. So it gives us an additional stabilizing force on our slice of soil that will restrain failure. Now, in order to determine these pull-out forces, we follow the conventional process. So it's a key element to the analysis. and would use slightly different rules for undrained and drained soils. So in the undrained case, if we have a length of reinforcement, this red bar here, and we're trying to pull it out of a body of soil, if we want to determine the pullout force T, then we need to know what are the shear stresses that are going to be mobilized on the interface between the reinforcement and the soil. So they're going to be mobilized on the top and the bottom faces of that reinforcement, and it's going to be a function of the shear strength of the adjacent soil. Typically, it's going to be a bit less than the shear strength of the soil, so we have an adhesion factor alpha, which might vary between 0.6 and 0.9, and we multiply that by Cu and assume that that is the shear stress at failure. So for the whole overall length L of reinforcement, the pullout force is going to be twice. So the factor 2 there is to account for the top and the bottom of the surface, multiplied by alpha Cu, that's the shear stress on those surfaces, multiplied by the length of the reinforcement. And that's per unit width into the diagram. For drained soils, we adopt a very similar process. We again still need to know what the shear stresses at failure are on the reinforcement. This time for a drained soil, the shear stresses are going to be a function of the normal stresses. So we have a shear stress assumed to act on that interface of alpha. Again, it's an adhesion factor multiplied by the average normal stress, sigma dashed n, acting normal to the reinforcement, multiplied by tan phi dashed. Otherwise, it's a very similar equation as to the undrained case. So again, for a length L of reinforcement, the pullout force is going to be 2 alpha sigma n dash tan phi dashed. Now, this requires us to calculate the effective normal stress, or the average normal stress. And in hand calculations, and for horizontal reinforcement, that's typically taken as the weight of overburden at that depth per unit area, and doesn't account for stress changes in the soil mass due to sliding failure. In the software, we can take account of that, so that is automatically dealt with by the software. Sorry, just going back a little bit. So we can apply these pullout force calculations, as we've seen already, to slip circle and also wedge type analysis. And these are commonly used, but those require a number of assumptions and are somewhat limited to the geometry considered. The LimitState GEO software uses a very different approach, which avoids assumptions and can determine the critical failure mode regardless of geometry, but essentially models the same underlying principles of reinforcement action that we've just covered here. So before we look at reinforced soil problems, we'll just have a quick look at how LimitState GEO itself works first. So the software works by using a method called discontinuity layout optimization. That's a rapid and direct means of analyzing the collapse state. We don't have to do an incremental analysis to approach that collapse state, as we would have to do in finite element elastoplastic methods. It was published back in 2007 in the Proceedings of the Royal Society, and there have been a number of other publications since then covering the methodology. And it's quite straightforward to describe it in its basic form. So I'll just do that here now. So we'll look at a very simple problem of just a rectangular block of soil. We've got a load on the surface and fixed boundaries to the left and to the base. In contrast to finite element methods, where we discretize that body into a set of elements, we populate the problem with a set of nodes. So here we've used a 3x4 array of nodes. And what we do essentially is we connect every node to every other node with a potential slip line. So here we've got 12 nodes. So we have 12 times 11 over 2, 66 potential slip lines. And then we use optimization to select out of those 66 lines, those lines that form the critical collapse mechanism that dissipates the minimum energy. And that turns out to be these 6 lines forming this very simple two-wedge mechanism. Now, with modern optimizers, we can be solving problems with millions of variables and millions and millions of potential slip lines. So typically we're going to be working with 500, 1,000, 2,000 nodes and correspondingly millions of potential slip lines. And the key thing to note is that the more nodes we have, the more potential connections we have, and essentially the richer set of potential slip lines we have for the optimizer to pick out from the critical collapse mechanism. So how does that work with reinforcement? Well, we can capture several modes of reinforcement failure and interaction. So just looking at this, going from the bottom upwards, at the base, you can see that we have a reinforcement element that is embedded firmly into the stationary soil mass to the left, and the sliding soil mass is essentially sliding past it. And that's going to induce shear forces into that reinforcement, trying to pull it out. The reinforcement is going to try and oppose the movement of that sliding soil mass. For the second piece of reinforcement from the base, what I've done in the model is actually set it to have a very low tensile strength. So here we can see it failing. It's basically not being pulled out at either end, but it is effectively stretching in a ductile manner. So the software models failure. It's a plastic failure, so we're modeling a ductile stretching, if you like, of the reinforcement. But that's a plastic failure mode. And the third piece of reinforcement from the base upwards, this time its length in the stationary soil mass on the left-hand side is very short. So basically the sliding soil mass to the right is going to pull that reinforcement out of the stationary soil, again inducing shear stresses in the reinforcement that gets transmitted into the sliding soil mass. And then this is happening for all the reinforcement, but for the top one, we kind of highlighted that there are several wedges effectively around this reinforcement. So each wedge is moving at a slightly different rate relative to the reinforcement. And that is all automatically taken account of by the software. So the software is still using the same rules of thumb, same basic equations that we covered a few slides ago that are used in conventional calculations, but it's able to do those, apply those automatically to problems involving not just one wedge, but thousands of wedges. So that's an overview of the discontinuity layout optimization software. It basically generates slipline mechanisms formed of effectively thousands or hundreds of sliding wedges, and can integrate that with the conventional approach to modeling soil reinforcement interaction. Clearly, it's important to be sure that the software is generating the right answers. The software itself has been verified against a wide range of closed-form solutions and benchmarks from the literature. Every time the software is altered, it runs thousands and thousands of tests to ensure that it's still getting the correct results. And we've posted about 100 of these on the website. So if you go to that web address, you can have a look at a whole range of benchmark problems. I've just put one example up here, which is of a reinforced slope, and comparing a DLO analysis with limit equilibrium using a log spiral mechanism. So log spiral mechanism gave a factor of safety of 1.5. The DLO analysis came out at 1.42, slightly lower, which we'd expect because the DLO is able to find more critical collapse mechanism than is determined by a single log spiral. Okay, so how do we actually go about modeling two-dimensional reinforcement in LimitState GEO itself? So let's look at the practicalities of using the software. So we model planar sheet reinforcement using what's called an engineered element in the software. So this is a particular material type which we apply to boundaries, as we'll see in a moment. And we specify this with 0 bending strength to represent a flexible geotextile or geogrid. We specify the reinforcement interfaces directly. So this is the properties, the shearing properties on the top and the bottom of the reinforcement. Those can be directly specified either in drained or undrained parameters. So CU or alpha CU or alpha tan phi essentially. And the software is able to model differential shearing above and below the reinforcement if that is what happens. And the normal stresses are determined inherently by the analysis. No need for an approximate estimation of that. And that essentially means that we can model both pull-out in either directions and sliding on a reinforcement layer or a more complicated combination of interactions. And we can also specify tensile rupture strength for the reinforcement. So that's the stress level at which it starts to plastically stretch in a ductile manner. So we're going to look at an example of a reinforced slope. So we're going to look at a problem here with some reinforcement set up according to a standard design guidance approach. So typically we want to know how long does our reinforcement have to be, how many reinforcement elements do we need to put in, how high a slope can we put in, and how strong does that reinforcement have to be. So a common analysis approach would be to use a slip circular method of slices, such as indicated here. And that works pretty well, but it's not going to be able to capture all possible failure modes. So I'll have a look at how we work that in the software. So I'll just bring up the software. So this is the standard software as it, once you open the file up, of the software up, we have a number of buttons along the top for controlling various display functions, drawing functions on the left, and various panels. I'll describe those as we go along. What I'm going to do is work with a predefined model here. So here we have a diagram of that slope problem that I showed you before. And we've got two soil bodies here. So we've got a soil body here. Everything I click on in the software, its properties appear in the property editor on the right-hand side. I won't go through all the parameters there, but we're going to look at the material that's in the soil body. It's called fill, and it's got a C dashed of 2.5 and a phi dashed value of 35. And then we have some base fill down here, which has similar properties, but unit weights of 20. So we can ask the software how stable is this problem. We can do that by looking at what's called a factor load or a factor strength approach. Factor load will tell us how much larger a load in the software has to be to cause collapse. Factor strength tells us how much we have to reduce the strength of the soil to cause collapse. So I'm just going to click solve. That's all we need to do for the software. And it quickly runs through a set of potential failure modes, identifies the critical ones. This is quite a shallow surface failure. And we see that we get a result of what's called the adequacy factor and strength of 0.555. Now, if I click on that, it'll explain what we've done. So essentially, we have two materials with C dashed and phi dashed values as specified as 2.5 and 35. We're not applying any partial factors, so the design values are the same. But what the software is saying is actually they're not strong enough. You actually have to divide those values by 0.55 to get values of 4.5 for C dashed and 51 for phi dashed for this slope to actually be stable. It's obviously very steep. There's not enough strength there in the soil for it to stand up on its own. So this adequacy factor is effectively a factor on strength, and if it's less than 1, it means that the problem is unstable. If it's greater than 1, then the problem is stable. Now, before we go and look and see how to apply reinforcement here, I mentioned partial factors, just show you how that's applied. So in the analysis option here, if I click on Scenario Manager, I can choose to change partial factors on my actions and material properties, or I can pick a predefined set. I'm going to pick the Eurocode 7 Design Approach 1 Combination 2 set. So you can see that that gives me factors on actions, and in particular, factors of 1.25 on C dashed and tan phi dashed. factor of 1.4 on CU. So again, if I solve the problem, those factors are pre-applied before we do the analysis. We come up with a very similar collapse mechanism as before, and this time our adequacy factor has dropped. I would expect it to get lower because we've added these partial factors to our soil strengths. And if we look at the way the software's worked it, characteristic values are the values we put in originally. The design values are the values with the partial factors of the Eurocode partial factors of 1.25 applied. So the C dashed of 2 and a phi dashed of 29. And then those have to be divided by this 0.44 value to get to the value that is required just for this system to be on the point of the collapse. And those values are the same as we had before. All we've done is apply partial factors. I'm going to work with unit factors just for simplicity. So we'll go back to unity factors for the rest of the demonstration. And what I'm going to do is just add in some reinforcement to the problem. So I'm going to first of all create an engineered element. So I can use this using tools, create new material. I can pick an engineered element. I can give it a color, give it a red color. Click the right OK button. I'll call that geotextile 1. And I'm going to pick a geotextile material property. Sorry, clicked the wrong button there. Geotextile, yeah. So for geotextile, essentially, we have two sets of parameters for an engineered element. This first set of parameters, pull-out factors and lateral factors, are only relevant for one-dimensional soil reinforcement. So if we're modeling a two-dimensional reinforcement, we don't have to worry about those values. The software, when I selected geotextiles, automatically applied these values of 1 times 10 to the 30, which is effectively infinity in the software, to TC and NC, and that's enough to make it behave as a two-dimensional reinforcement. The parameter we're primarily interested in down here is the rupture strength, or tensile strength of the material. So I'm just going to set that to 80. Clearly, flexible reinforcement has no compressive strength, and if it's flexible, it's going to have no bending strength, so those are automatically set to 0. So I've created that material. I'll click OK. I then have to apply that to the model. So I'm going to click on this button here, which allows me to draw a boundary line. I'm going to start somewhere over here and just draw a line back to that position. And we're going to add a vertex here. So click on that button. That allows me to break that boundary line into 2 parts. And then I'm going to take this geotextile and drag it and drop it on to that. So I've now got a length of reinforcement in the middle of this soil there. And then I need to create another material. So that's my reinforcement, but I need to create the material that defines the interface strength between the reinforcement and the soil. So again, I go to Tools, Create New Material. This time I'm going to create what's called a derived Morcullo material. I'm going to leave that color, and I'm going to call it interface. And for a derived material, we define it into its properties relative to an existing material. So the reinforcement is installed in the fill material. So I'm going to choose that one, fill material. And basically, we put in multipliers on the cohesion and angle of friction, or tan phi values, for that original material. So if we've got an alpha factor of, say, 0.8, then we simply type in 0.8 here, and that means that this derived material, its strengths are 0.8 of the value of the strengths of the fill material. That's okay, and then I can drag and drop that onto the material. I'm going to click Add, and now that, I just zoom in there, you can see the green material either side of the red, and that's indicating that we've got the reinforcement there. And if I click on the element, its properties appear on the right. And we can see we've got material on the top, which is interface, the engineered element. So one I've just created, and below we've got the interface material again. So they're all in place. And if I just zoom back in, or zoom back out rather, we can solve that problem. So I click solve. And what happens? Well, effectively, we've put some reinforcement in. We've inhibited the full height mechanism. All we've done is actually create a miniature version of that mechanism. And software is just going to pick the most critical parts. So the upper layer is fractionally taller than the lower layer. And that's where we're going to get that failure mode. But we have increased our adequacy factor because of that reduced height. And we're getting closer to 1. We're now at 0.7 rather than 0.5. And the software also calculates the axial force in the reinforcement at the point of failure. So we can click on this little graph in red and hover on any point, and it will tell us what the how the axial force is varying. And that's at the point of failure with this adequacy factor, this modified strength applied to the parameters. Now, if I wanted to reinforce that slope, then I would add a number of layers to that. I'm not going to do that now for reasons of time. What I will do is open up a file that we already prepared that has that in. So I've basically added in all that reinforcement. I've got my interface. In this case, it's colored blue, but essentially we've got the same setup, exactly those same parameters that I just showed you. And I can solve that problem again. Turns out it doesn't give a very exciting solution. All that we've done is we've forced the critical failure is now found to be at the very top layer. And the adequacy factor is now above 1. So if I click on that value, we can see that I put in the strength of the soil is 2.5 and 35. For the interface, it's 2 and 29.25. And for this system to collapse, these strengths actually have to be reduced, and they're reduced by that factor 1.228. That's a kind of, that is the critical failure mode we'd expect. It's just finding its way in between or between the reinforcement elements. However, just to show that we can capture other modes of failure, I'm going to change this base materials properties. Sorry, I just clicked on that solution. That shows me all the stresses that are acting on that block. So if I click here on the base fill, we've actually set a CU value of 40. So I'm going to change its behavior from a drained soil to an undrained soil. So I have a setting here. I can set it to always behave as an undrained material. And then if I solve, we should end up with a base failure essentially for this reinforced slope. So in this particular case, solved, it's nearly got there, okay. What we can see is that essentially the reinforcement has made that front part of the slope behave a bit like a wall, as we'd expect, and we're getting failure behind that predominantly, and also failure underneath. So we're getting essentially a bearing failure of this reinforced mass of soil. But in this case, we still have an adequacy factor above 1, so that is stable. Just to show you that the software can model a more complicated interaction between soil and reinforcement, I'm just going to pull up one more model here called where we've essentially optimized the layout of the reinforcement. So this is an area of research recently published in Geotechnical, which basically uses the optimization built in to this methodology, the DLO methodology, but tweaks it to also optimize the length of reinforcement to give you the minimum amount of material required to give you a stability, to put this slope essentially on the point of failure. So we've got varied lengths required depending on how the failure mechanism interacts with the slope. So if I solve that one, what we should find is that we get a much more complicated interaction with that reinforcement. Essentially, we're using the full the reinforcement to its maximum in all places, and that means the failure mechanism is going to interact fully with that reinforcement, as we can see here. So I think we're pretty well at that solution. Software just has to iterate around a little bit to get to the critical value, and there we have a much more complicated interaction going on. And we've got an adequacy factor just above 1, which means that this is stable, just slightly above that point at which the slope goes unstable. So that illustrates hopefully the kind of ability of the software to fully model many wedge problem interaction with the reinforcement. Okay, so at this point, we'll wrap up the demonstration with LimitState Geo and revert back to the presentation. So hopefully what you've seen in this short presentation is that in terms of modeling planar reinforcement, we've got a generic implementation available in the LimitState Geo software. It's been calibrated against Methodist slices and a slip circle log spiral analysis. The recommended approach to modeling two-dimensional geosynthetic reinforcement in the software is to use an engineered element with a specified tensile rupture strength of R, and combine that with interface materials defined above and below the element using an appropriate alpha interface factor. And these are easy to implement using the more Coulomb derived material in the software. But both those materials are assigned to the same boundary material in the model. And just to focus in on these engineered elements, they're general purpose objects that we can also use to model one-dimensional reinforcement, or anchor tendons or sheet pile walls. Their specific behavior is controlled by pull-out and lateral factors T and N. For general two-dimensional reinforcement modeling, those values are simply set to infinity in the software. And to model a flexible geotextile, we set the moment of resistance to 0 and the compression strength to 0 also. And that allows us to model that flexibility in the geotextile. So just to wrap up, hopefully you've seen that reinforcement modeling in LimitState Geo uses the same mechanics as conventional methods, such as slip circle or wedge analysis, but effectively allows thousands of wedges to be modeled. There's no need to separately consider internal, external failure, pull-out lengths, or reinforcement rupture. Those are all handled automatically. And the software automatically searches for all possible failure modes every time you solve. Hopefully you've seen that the workflow is straightforward from geometry import to reporting. We haven't illustrated all of that, but you've got an intuitive user interface that puts user into control. Just solve the problem with one mouse click. Very easy to handle partial factor application. Hopefully you've seen it's a very interactive tool. It solves quickly, so many of our customers use LimitState Geo interactively to answer what-if type questions. And it empowers you to essentially get a better feel for the problem. You can play around with the parameters and see what is significant, what's a critical parameter, what's a less critical parameter. And the one piece of software can solve any ultimate limit state problem type. So there's no need to impose idealizations or correction factors for non-standard geometries, and no need to learn how to use many different programs. So that takes us to the end of the webinar. We've got a few minutes for questions. So we'll just see what questions have been posted. So we've got a question. What would a geotextile failure look like in the software? That's probably easiest for me to go back to, no, actually that software, probably just back to the slide. Here. So if the geotextile itself is failing in tensile rupture, then effectively in an animation, you're going to see it stretch like this. You can also determine sorry, just go back to this problem. And if it is failing in rupture, then we can also plot tensile force in the reinforcement, and you can look at that. And if that tensile force or axial force equals the strength of the tensile strength of the reinforcement, then it's also that will be the point at which it is failing. So you can look at it in two ways: in the animation, if the element is stretching, but also you can look at these graphs of forces and check to see whether they've reached the failure load. Got another question. How do we determine the appropriate alpha factor to use? That one's harder to answer. That's really down to your soil investigation and the type of geotextile that you're using. And there are various guidelines to determining that factor for that interaction. Typical values are between 0.6, 0.9, but it very much depends on the nature of the geotextile and the soil that you're working with. Another question is the software available free? Unfortunately not. There is a license fee to pay for using the software, but we're very happy to provide trial versions for you to try out if you wish to. Okay, I think we've run out of time at this point, so we're going to wrap up there, and I'll hand back to Tom just to finish off.
Thanks, Colin, and thanks everyone for joining us today. We do hope you found the webinar informative, and as I mentioned at the start, if it has prompted any additional questions, please do get in touch via telephone, or you can email us on info@limitstate.com, and we'll be more than happy to help. If you'd like to watch the webinar again, or if you think you might know somebody who would be interested to see it, there'll be a recording available in the next day or so on our YouTube channel, and we'll email you with a link once it becomes available. LimitState GEO itself is available to download and use in trial mode via our website, and the address is limitstate.com/geo. And do also be sure to follow us on LinkedIn and Twitter to be kept up to date with all of our news and be the first to get notifications of our upcoming webinars. So lastly, I'd just like to say thank you all for listening, and I hope that you can join us again for one of our future sessions. Goodbye.